It's a great pleasure to be here. It's amazing to be 60, but you will learn about this in your personal life also. Yeah, I'm going to talk about, first of all, I'm a professor at the University of Freiburg. The IMTech is really part of the university. And Hahn-Schickard is a non-profit organization outside university. And so I decided to talk today about the adventure of commercializing microfluidics. As Holger is not here, I thought I should maybe fill in. And there's a subtitle calling Riding a Roller Coaster in an Adventure Park. This is more or less what I experienced in the last 30 years. Now, how did I start? I started in 1991 as a PhD student, and at that moment there was no microfluidics. There was only a field called MEMS, microelectromechanical systems, and most of the people there were doing sensors, mainly for automotive industry. And they told me at Fraunhofer Institute at that time, if you develop a micropump, there will be hundreds of applications for micropumps. And so I developed an electrostatically driven micropump, can be seen here, very small. And it worked like this, so it has 4 chips. It was electrostatically driven, a membrane. If you apply a voltage, you can attract the membrane, and you have 2 check valves directing the fluid. And that was my PhD. Actually, it also worked. So at low frequencies, we found what we have expected. So we could increase the pump rate by frequency. And then we found something interesting. If we go to frequencies above few kilohertz, the pump changed the direction. So it was a kind of a dynamic phenomenon, a resonance phenomenon, and we had a backward mode. And actually, that is my very first real paper in '95, a bidirectional silicon micropump. And when I looked it up recently, preparing this talk, I realized this is the most cited original work that I've done, get the most credit. But there's absolutely no use for micropumps, in my view, up to now. Yeah? It's amazing. So I also used the technology, the same technology, electrostatic actuation, in order to work on valves. And actually, this is a 3-chip device. If you switch on the power, you can move a valve plate here in the middle, as you can see. And that changes the pressure at the working port between 0 bars and 10 bars. So it was quite powerful, controlling 10 bars of pressure. But again, when I tried to talk to people using that, I realized that my developments were more expensive than the state of the art. So they could do amazing things, but in standard technology, you could do the same things cheaper. So that was a little bit of frustrating to me. Even when I have to say there is one exception. So end of the 90s, we sold 1,000 valves to Max Planck Institute, active in space research. And they loosely told us what they are aiming to do with that, but we forgot about that. And then we realized almost 15 years later, there was a space mission to a comet. So the mission was 10 years in space before it hit a comet. And on that space mission, they had 28 of our electrostatically driven microvalves on board to control the gas flow in a gas chromatography. So it was too expensive for everything on Earth, but it was still useful for something in space. But anyway, my conclusion in the mid of 19th was that we had micropumps and microvalves without fitting a real-world application. There were many people come to us, oh, we need micropumps, but if you look into the details, it didn't fit. And at the end, they need something different. So that was my experience. And so I decided I should more focus on applications, starting with the application first, using microfluidics as a toolbox, and then designing the microfluidic systems based on what I know from microfluidics and targeting an application. I will give you some examples what we did at the late 90s. So one of the first projects, a big project, was developing an electronic fountain pen together with the company Lamy. What you probably don't know, if you go into an airplane with a fountain pen and there is a critical fill level of the ink, They reduce the air pressure in the cabin, and the air expands, pushing out the ink, and so it can leak. So this was one problem that we were targeting. At the end, we developed the microelectromechanical systems here with valves and so on. And 100 of those fountain pens have been produced, but it never entered the market. So the company was sold to a different owner, and he decided to stop there. Second project was with Eppendorf. End of the 90s, enzymes were quite expensive. 1 microliter of enzyme, you had to pay something like 20 euros or so. And the idea was to deliver nanoliters of enzymes in order to save money. And it was a good business model.
They are still very expensive.
But not as expected. And we developed the technology, I don't go to the detail, we could deliver a liquid jet independent on viscosity, independent on temperature at a very high precision. And but it ended up with prototypes, never entered the market, but was base of what we did later. And then at the end of the 90s, there was the biochip hype or microarray field. There were companies like Affymetrix creating a lot of inspiration in doing highly parallel analysis. And we developed the technology printheads where you could fill in different liquids. For example, here 24 different liquids, 96 different liquids. They were connected to an array of nozzles, and we could, in a non-contact manner, deliver droplets from that printhead. Different liquids. And it was very interesting. We also developed the fabrication line for microarrays, about 300 microarray chips per hour with 1,440 different reagents on it. So it was quite a big effort. And then happened that at the late 90s, first of all, I have to explain how the feeling was in the field. So there were many biochip conferences, about 4 to 5 conferences a year. And if you gave presentations at those conferences, at the end, venture capitalists came to you asking if you want to have money for doing a company based on this technology. This was completely crazy. And in my town, in Freiburg at that time, there were 4 people, they took money. They created a company called Biochip Technologies, and they grew from 4 people in 97 to about 300 people in the year 2000, so it was exploded. And they used our TopSpot technology, they promoted the TopSpot technology to get money from the stock market we didn't have any connection to them. Well, we didn't have any profit out of this, but they made a lot of money out of that. Good. Then in March 2000, 20 years before the pandemic, the dot-com bubble collapsed completely. So there was a new economy hype at the stock market, and this completely collapsed. The microarray hype was also over. And GeneScan, for example, they reduced from 300 people to 30 people. And again, we had devices and technologies without a real application because the application was gone. It was a hype. And so nevertheless, we decided that we want to found a company called BioFluidix using our technology, the printing technology, and but starting without any venture capitalist, as we have learned that this is a crazy business. And so we just started by selling the devices. And here I want to introduce Peter Kolter. He was the first CEO of the company. Andreas Ernst, the second CEO of the company, was our spin-off number 1. There's 2 technologies. The first one was the TopSpot technology that explained. And we saw that we should have more easy, more robust devices that the people can work with. And the most relevant product for the company was a thin polymer tube, only 200 micrometers in diameter. It's squeezed by a piezo-stack actuator, and it delivers small nanoliter droplets at, again, independent on viscosity and surface tension and temperature and things like that. So, of course, you cannot sell a component like a polymer tube. It doesn't make sense. So you need to have an instrument in order to have something that is, can be used by others. So we also developed those workstations. And then we started that company. And then we were approached by pharmaceutical companies, and they challenged us with a challenge: can you deliver single cells into single wells of a well plate? So a little bit like this: you have a well plate, and you dispense one cell, another cell, and so on. And we came up with an idea how to do that. Before I discuss this, we need to avoid empty droplets. We need to avoid that more than one cell is in a cavity. This is very dangerous in the field of cell line development. You need to make sure that only one cell is the mother of all cells that produces a certain drug. And it needs to be traceable. And this is how it ended up. We have a cartridge with a silicon chip, the same chip that we used for Eppendorf. And we fill in cells, and we have a camera looking at the orifice. When the cell is approaching, we can predict if the next droplet will be empty or contain a cell. If the droplet is empty, we have a shutter that removes the droplet. If there is predicted one cell in a droplet, we just let it pulse and move to the next cell. If there are more than one cell in a droplet, again, we remove it. And this is how you can see. It's one cell approaching after every droplet the nozzle area. Here is in the region of interest, and in the next shot it's away, so we delivered exactly one cell. We can also trace the cell in the well plate, see that the cells grows a culture. And at that moment, two PhD students decided to create a company, spin-off number 2, Cytena, delivering individual cells into well plates. And again, I would like to highlight these guys here. They were PhD students. And now the next spin-off company was Cytena Bioprocess Solution by Cheng-Han Tsai from Taiwan. He came with a technology-driven idea. He wanted to use shape memory actuators. And it took me 2 years to convince him that don't be technology-driven. Think about the application, think about the use. In the third year, he thought about, okay, I should do something that can do mixed well plates in order to stimulate cultures, cell culture and well plates. He founded a company in Taiwan because he was Taiwanese. When he went back, he received money from Taiwan in 2019, number 3. And then happened something very crazy. We were approached by a Swedish company. The Swedish company were only 2 years old. It was younger than our companies. And they offered 30 million euro for buying Cytena. And the deal was 10 million euro in cash, 20 million euro in shares of selling. And we thought about, okay, we never know what this crazy company is doing. The shares, you don't know if it's any value in it. We take the 10 million, and that is it's a very good story, first exit of a company. And then the roller coaster story continues. The discussion of selling was they wanted to print organs. Yeah, that was the story at the stock market. And you see the development of the share value. This was the moment when they acquired Cytena, paying by their company shares. And then you have a certain period of time where you cannot sell the shares. This was the first moment where we could sell part of the shares. And the value of the deal increased from 30 million to 60 million to 160 million euro. And then it dropped down to 60 million, and now it's 25 million. So it's a crazy roller coaster story with just a hype in the field. And after the microarray hype, this was just another hype where we were in quite luckily. Now, my people in the lab told me, is it honest to sell a company for such amount of money from the PhD students just working next door after 5 years of creating the company? I told them, well, it's important in my view that not only musicians or sportsmen make money with their talent, it's also important that as a scientist or engineer, you have at least a chance to make money out of your knowledge. But of course, you need a huge amount of luck, and at the end, it's a lottery. And we were just profiting from the bioprinting hype. Yeah. So luckily, in 2022, we also sold BioFluidix to the company Hamilton. And after promoting for decades nanoliter dispensing, and nobody wants to have nanoliter dispensing, it it changed the field, and now Hamilton, known for pipetting workstations in the microliter and milliliter range, they acquired nanoliter and picoliter capabilities, but 70 years after creating that company. So that was the first part. I'm not sure how much time it has. There was another direction in my lab, and this was what I say, it's the search for the holy grail in microfluidics. And what is the holy grail in microfluidics? In my view, as you all know, microfluidics is a quite diverse field. You have next generation sequencing, single cell sequencing, organs on chip, bioprinting, so there are different fields. And in my view, when I started 30 years ago, the holy grail was rapid diagnostics of complex diseases at the point of need, as also Holger has shown it. And so what is the challenge? You have to do assays that run on complex instruments in centralized facilities. You put it to an instrument at a point of care, and everything is done in a chip. And the question is, was that possible? Many challenges. You need to be robust, sample-to-answer systems, same precision as in centralized labs, complex biochemical assays. It's very cost-sensitive, and it's also time-sensitive, because the advantage in time to result is the only advantage you have in this approach. And though we looked up what are the right microfluidic platforms for doing that, and we actually wrote a paper on microfluidic platforms, and this is the gold standard, the lateral flow tests. And we wrote that paper, and you see many different technologies, and we focused on centrifugal microfluidics, and I will discuss it later. And actually, this is the most cited paper that I produced in my career. So what is centrifugal microfluidics? You control a process on a chip just by spinning the chip. So more or less, this is a centrifuge. This is a chip or a cartridge. You put the cartridge onto the device, and you just centrifuge. And by changing the spinning frequency, you can control the processes that happen on the chip, like releasing a buffer, doing mixing, aliquoting, PCR by changing temperature, and so on. And that's it. So you do not need any micropumps, tubings, no pipettes. Just put a sample, put the cartridge through the instrument, and that's what you do. If you think about what do I need to control on the chip, there are many microfluidic operations, reagent supply, valving, timing, aliquoting, mixing, metering, all those processes needs to be done on such a chip. And our design philosophy was always keep the disposable as cheap as possible. And all unit operations, you have to have a solution in a low-cost disposable. And so the chip, in our case, always looks like this. It's one microstructured part with channels and reservoirs. You fill it with reagents, and then you seal it with a thin polymer film, and that's it. So the chip needs to be cheap and simple, and that's it. And then in 2016, six other guys from the lab decided to create a company out of it, SpinDiag, and they were working on drug-resistant bacteria in hospitals. And they had the technology to do that in 30 minutes to screen the patients when they enter the hospital in order to separate those bringing MRSA into the clinic from the rest of the patients. And they worked for 4 years, and then they had were close to a very first product in 2020. And then a different pandemic came, as you all know, COVID-19. So it was really a kind of tsunami. It was changing everything. And so they switched with the same chip to a different target, to COVID-19. And it was this is the essay, by the way, but I don't go to the detail, what the chip is able to do, and you see where it's done on the chip. And it was really, again, a roller coaster story. We didn't have any supplier of chips, so we had the challenge to produce chips for this technology. So we built up a kind of a fabrication line in our institute, working from 6 o'clock in the morning until 2 o'clock in the night by different teams, and ended up to bring that to the market in November 2020. Then we also transferred to a production line at the German company RKT, doing with robots, able to do it in a low-cost manufacturing, about 50,000 PCR tests per month. And at the end, in 2023, so the SpinDiag had different cartridges for different diseases. And they produced 1 million cartridges for 240 German hospitals. One cartridge was about 30 euro. So they had a total turnover of 30 million euro. And in the lab we were working, the time to result was 50 minutes at the beginning. And in the lab we were improving that. We achieved 15 minutes time to result of a COVID RT PCR test at the end, with just slightly changing the cartridge and the menu. And then, of course, roller coaster. Life is a roller coaster. The pandemic came to an end. The German policy changed on COVID testing on February 28 in 2023. The COVID-19 market collapsed within a week, so there was no sales anymore. And 120 employees in the company didn't have a job anymore, so SpinDiag had to file insolvency. And so it was like finding the holy grail of microfluidics, and the worst of it is nothing. It was a really frustrating period, but of course we always look forward. This is, I mentioned another roller coaster story, so there were many roller coaster stories. But luckily we had two more spin-offs, Dermagnostix and Endress and Hauser Biosense, two further spin-offs focusing on different fields of application using the same technology, and they acquired the assets of SpinDiag. So spin-off number 5 is Biosense. So they look to molecular diagnostics or molecular analytics in water and wastewater, food, beverages, life science, and so on. And they use the SpinDiag cartridge with a 2-stage PCR without sample purification. They have a different one, including sample purification on the same instrument, now trying to establish this in different applications. And another startup, number 6, Dermagnostix. So they have molecular markers to differentiate between psoriasis and eczema, two different diseases that look, but one of them can be treated in a very costly treatment, and so they can do a differentiation based on an assay that they have. Instead of half disc as SpinDiag, they have a full disc because they also have the need DNA extraction from a tissue sample in paraffin, which is more complex. I don't go to the details. And then at the end, we thought, okay, we found the Holy Grail, it's worth nothing. Maybe there's a different Holy Grail, and continue to search. And we combined two new fields two new trends in the field. And the first trend is going from qPCR assays. You have a certain number of molecules in here, and in order to quantify, you need calibration, which is challenging. To the digital PCR world, where you split the sample into millions of compartments, you do an amplification, and then you just count the number of positive compartments. This is an absolute quantitative measurement. It's a very interesting technology. And we combine that with a new target molecule. So we have done DNA, we have done RNA, but so far it's very challenging to identify individual proteins in a sample. And so we want to target also proteins in the same limit of detection as DNA. And this is now spin-off number 7. You again see Peter Koltai. And it combines digital PCR with protein detection. I will explain how it works. So if you want, for example, to test if two proteins are reacting with each other in a sample, we use two antibodies. Let's say a blue antibody for the blue protein, a yellow antibody for the yellow protein. Both antibodies are labeled with DNA, and the assay is only mixing. Yeah? And then after that, we do a dilution. We split it into compartments, and we do a PCR. That means if you have a blue antibody, you will have a blue color. If you have a yellow antibody, you will have a yellow color. And if you have both antibodies in the same droplet, you have a green color of mixture of both. And then you count. You count the yellow droplets, the blue droplets, the green droplets, the empty droplets. and by doing mathematical calculation, you can calculate back how many interactions did you have in your sample. And based on the technology, you not only can count interactions of two proteins, you can also do one protein with two antibodies, or activated protein, or activated protein reacting with another protein, and so on. And just give one result, which was recently published on signaling pathways in cells. So this is the cell membrane. You have receptors on the cell membrane. This is the pathway of biochemical reactions in the cell. And we were able to do an 8-plex assay on this, in this sample. And now you can quantify, if you give a certain drug, for example, to the cell, how much difference will you have between the native cell and the treated cell. And you can do really quantitative analysis. You see that this pathway, for example, is very much suppressed, and you have an increase here, you have an increase there, and you have a complete, fully suppression of, for example, this protein-protein interaction, the cell membrane. So you can quantify the amount of proteins in individual cells by this technology. I have a spin-off number 8. I don't go into the details. It's about electrolyzers and fuel cells, and it has, you might say, this has nothing to do with microfluidics. We came into the field by just doing inkjet printing of the core component here, and we realized it's working better, and don't go to the details. So at the end, now after 30 years of doing research in the field, so we have quite many spin-off companies. Some of them did very well. So in overall, they have created about 200 jobs in the region of Freiburg. Some of them failed. Very pity, very strange. It hurt a lot, but that's life. And I want to use one slide in order to promote that doing application-oriented research is not in conflict with academic careers. So these are the people that got professors out of the lab. In 2008, Jens de Cree, Felix von Stetten, Sven Katzenmacher, Simon Thiele, Niels Braust. And so it's not in conflict. We were always able to publish, and I would like to promote that if you think about should I be more application-oriented, should I be more academic, for me it's not a difference. And come to an end. And one guy, Peter Kolter, he got the professorship offer in 2005. He rejected in order to lead BioFluidix, got a serial entrepreneur, and he's the first to retire at the age of 55 last year. And it was very good. One more spin-off, the government realized that we are doing things that end up in jobs, so they gave us a lot of money in order to build a new institute, the Hahn-Schickard Institute of Microanalysis Systems. This is just under construction. We are moving in 1 year from now. And that's not the end. 3 more teams are on the way because they got inspired by their colleagues, and now maybe too many people want to create a company in the lab. But again, we have a company called Million, or they are on the way to form the company Million Molecules, doing digital PCR with 10 million compartments. I realized, Abe, that you did that 14 years ago.
1 million.
Or 1 million. So a very easy process in 10 minutes, they can do a PCR. C. Sparta was the founder of Cytena again. So he almost retired. He didn't work for 3 years. And now he's coming back to the lab as 10 years ago as a PhD student. He wants to do another startup, very amazing, about high throughput screening employing cell-based assays. And Victoria trying to sell organoids for drug screening. So very interesting. Last slide. What are, in my view, success factors? It's the passion for the project. And I never selected PhD student depending what they did before. I always tried to speak to them, and if I feel the passion of their work that they did in the work before, they were the right people for our lab. The commitments of the PIs. Don't do a project where you are not convinced it makes sense. So if you really feel the commitment, that's a very important requirement. And of course, having luck. It's sometimes like a lottery. And I will end up with this slide. I'm not sure if you know the movie Forrest Gump. The 60-year-old guys know that probably. It came out in 94. It's also 30 years old. And Forrest Gump, he discovers anything, yeah. And he was sitting there saying, my mama always said life was like a box of chocolates. You never know what you're gonna get. And this is also what my final statement is. I never could see if something is running into a real important development or not. Just do it as long as you are confident with it, and if you're not confident anymore, then stop. That is my slide. Thank you very much.